In the last three experiments, we learned how to draw on the canvas. Then we learned how to manipulate the canvas through keystrokes, and finally how to manipulate the canvas by way of mouse movements. In this experiment, what we're now going to do is animation in real time. And that is, we're going to create animations that do not require user input, but simply move things around basically on time. Our new piece of code is going to use what's called a timer or an interval timer within JavaScript. If you look at our code, the first line up here says set interval timer to 500 milliseconds. Every 500 milliseconds or every half second, it's going to call this function called timer. Then down here, we have our redraw function, the same redraw function we had in the last experiment. And then down here, every time the timer is called, it's going to increment X by 10, increment Y by 10, and call redraw. Let's take a look at that. There's our rectangle moving steadily across the screen under its own volition, no keyboard or mouse inputs at all. Let's look at that again. This is nice, but wouldn't it be nice if we had more than one object on the screen? In our next experiment, we're going to draw two different rectangles at the same time. As you can see, this is the interval timer that we had before, but now we've got a new set of variables. We've got color 0, x0, y0, width 0, and height 0. And these are the coordinates of our red square. And we've also got color 1, x1, y1, w1, and h1 for our green square. And then I have two methods, one to draw our red square and one to draw our green square. And then I rewrote the redraw function to clear the screen and then call redraw 0, which draws our red square, and redraw 1, which draws our green square. Let's take a look at what that looks like without our timer turned on. You can see here that we have our big red square in the upper left-hand corner of the screen and our smaller green square in the lower right-hand corner of the screen. And that's thanks to our redraw function. It cleared the screen, and then it redraws 0, and it redraws 1. Now, when we turn the timer on, let's turn this back on, every half second, it's going to call the timer function. And down here, it does what it did before for the red square, which is it adds 10 to its x, and it adds 10 to its y. It's going to have the presentation of skipping along the diagonal from upper left to lower right, but then we subtract 10 from the x1 and subtract 10 from the y1. And so the green square now is going to trick across the screen from the lower right-hand corner to the upper left-hand corner. So let's watch that. Every half second, both of these objects are updated, and then we redraw. And let's look at that again. Watch what happens to the green square. It appears to be transitioning over the top of the red square, as if the red square were in some way behind the green square. And again, this is an illusion, right? We don't actually have two physical objects moving around in our canvas. What we have is two different rectangles, one being drawn after the other. When we call redraw 0, it redraws the red square first, and then we call redraw 1, and it redraws the green square second. And because the red square was drawn first, if the green square and the red square overlap, then the red square pixels get covered up by the green pixels. And it has the illusion of making a green square that appears to be in front of the red square. Imagine if we had, say, a dozen of these squares bouncing around on the screen, or even worse than that, 100 or 1,000. A very complicated game would have many objects, and they'd all be wandering around the screen under their own volition. The problem we have is that we have to create what are called scalar variables to keep track of each one of these. We'd have to have a different redraw function for each one of these squares. This is a lot of work for us, and fortunately, there's a way of managing it. And what we can do is we can create these objects inside of a list of arrays. And instead of having a scalar value of, say, _0 or _1, what we can do instead is use indexes. And indexes allow us to create loops and to address each one of the different objects by its index. Let's take a look at that now. We'll start using arrays. So now what I've done here is I've got an array of colors, red, green, and orange. I've got an array of x coordinates, an array of y coordinates, array of widths, an array of deltas. We'll talk about that. If I want to know where the red square shows up, I look at the 0th element. Remember, arrays are 0 based. Color sub 0 would be red, X sub 0 would be 0 and Y sub 0 would be 0. W sub 0 would be 100 and H sub 0 would be 100. That's my red square. It's in 0, 0, and for a width of 100 and 100. My green one is at 250, 250 for a width of 50 and a height of 50. And then my orange square is at position 200, 125 for a width of 50 and a height of 25. So it's a thin horizontal rectangle. Let's go ahead and take a look at this. I'm going to turn off the timer and redraw our screen. Here you can see the red square and the orange square and the green square down here a little bit off screen. I'm going to change this down to 200 so we can see it. And so how do we draw those? If we look at our redraw function, it clears the screen and then it goes through a loop from 0 to the color length, and it increments the index by 1. And then it calls the draw function with the variable I. So that is the index into our arrays. The draw function then does exactly what the old code did, except that instead of using color underscore 0 or color underbar 1, we now use the index variable n to index into the color, to choose the color that we want. When we want to draw just in fact, let's go ahead and do this as an example. Instead of doing this redraw, I can do draw sub 0, and it would draw the red square. And if I call draw sub 1, it draws the green square. If I say draw sub 2, draws the orange square. Rather than call those functions independently, which is what we can do, if we go into the redraw function, rather than do a loop, we could do this. We could call draw sub 0 and draw sub 1. And this is essentially what we did last time, except we used scalar variables instead of array variables. It draws the red and the green. Draw sub 0 draws the red one, draw sub 1 draws the green one. And if you come down here, when we pass in a 0, color sub 0 gets picked, it draws red. X sub 0 is the X coordinate of the 0th or the red rectangle, that's a 0. Y sub 0 would also be 0. Width would be 100. Height sub 0 would be 100. So it draws our rectangle as being 0, 0 for width and height of 100, 100. But when we call it with a 1, it draws the green rectangle, which is 200 at 200 for a width and height of 50 and 50. And then, of course, we could add another draw function in here and redraw this. And now all of our rectangles show up on the screen. But this is really a pain because if we add yet another rectangle, and we can do that just by extending our arrays, right? We can put this one at, say, 50, 50 for a width of 75 and a height of 60. Now, if I refresh this, notice that our blue rectangle did not show up. And the reason it didn't show up is because we didn't draw it. I can add that now. And this is a pain. Every time I add another object to our list of screen objects, I have to add another draw method. That's the reason we do this iteration, right? We set up this loop. We go from 0 to however many colors there are, and we assume that these arrays are all the same size, and we call draw on that function. I'm going to take this draw method out. We're just going to call redraw just the one time, and now it draws the entire screen. Now let's talk about the animation. In order to animate this, we did exactly the same thing that we did last time. We want to update our X and Y coordinates as necessary. And so every time our timer is called, we iterate across all of our array elements, and then we call the move function. And the move function, again, it takes an index, it takes X sub whatever, X sub 0, let's say, and then it takes that same value and it adds whatever our dx is. If we look at dx sub 0, it's 10. Remember, we move our rectangle 10 to the right and 10 down. That's the dy here. X and Y are incremented by that index value every time we call move. And I'm going to do this just one time. I'm going to do it just with the, there we go. I'm doing it just with the red rectangle. And so Now you can see the red rectangle moving across the screen. The other objects do not move because we only called the move function for move sub 0 for the red. I can, again, I can animate each of these in turn. Let's just do the red and the green. See how they move? And the others are stationary, but I want to move all of them. Rather than add a single command to move each of them, I iterate across all of them and call them one after the other, move them. And then once they've all been moved, then I call redraw. And what does redraw do? It clears the screen and then it iterates across all of the objects and redraws them. And that gives us the illusion of 4 objects moving independently across our playfield. And also notice that this orange object seems to be moving really slowly. And again, that's an illusion. And the reason the orange object is moving slowly is because its dx is only -5, whereas the dx for the other objects were 10. And also it's only moving to the left. It's not moving up and down because the dy was set to 0, right? It's not going to move. It appears to move from right to left because we're constantly decrementing its x value, but leaving the y value alone. And the poor blue square, its dx and its dy are 0, it appears to be stationary. Now there's one other thing to look at here. Look at that. It looks like this orange object is in front of the red and green. And remember, we talked about this before. When these 3 objects converge in the center of the screen, it appears that the orange object is in front of the green and the green is in front of the red and the blue is in front of all of them. And the reason for that is that we are drawing them from back to front. We're drawing the red, then the green, then the orange, and then the blue. And because the red is drawn first, it appears to be drawn in the background. This is what we call the Z order of the objects. The Z order is directly related to the order in which you draw the objects on the screen. And so we've drawn them from the back to the front. And so red appears to be in the back as being the 0th object. Green appears to be in front of red. Orange appears to be in front of red and green, and blue appears to be in front of all 3 of them. Let's watch that one more time. We still have a problem here. And the problem is that every time we want to add another object, we've got to update 7 arrays, right? We've got x, y, width, height, dx, dy, and the color. And I don't know about you, but I find it hard to match blue with its values because they're not directly under blue. In the next experiment, what we're going to do is add these 2 dictionaries. And a dictionary or a hash or an associative array is a way of grouping things together into one object so that they're all combined together. Welcome back. I've not changed our code at all. This is the exact same piece of code that we looked at last time. I did simplify the for loop, and I'll talk about that in a minute, but this is basically the same program that we looked at last time. The difference here is that now I've created an array of objects. You can see that's the array, and each of the objects is what's called an associative array or a hash or a dictionary. And all of these terms are correct. There depends on the context that you're working in. And what we've done here is we've got a label, which is the name here or the key, and a value. That's the way associative arrays work, is that they have a key value pair. And if you want to get at that key value pair, you use what's called a dot notation. Here, the first object is our red rectangle. Its color is red. It's at the x, y coordinates of 0, 0, with a width and a height of 100 and a dx of 10, 10. This is the exact same scenario we had last time. Here's our green object. It starts at 250, 250. It's got a width and a height of 50, and it traverses the screen from the lower right-hand corner to the upper right-hand corner by setting its dx and dy to -10. Our orange rectangle starts at 200, 125. Its width of 50 and 50, and its dx is -5, and its dy is 0. And then our blue square is this time at 250, 250. It's going to be moving at -20. I'm going to turn this back to 500. Again, we redraw the page, we erase everything. This for loop is probably simpler than the for loop that we saw before, where we used an index, but because we are now an array of objects, we can use the for each method of calling the for loop. And so what we're saying is for each object in objects, draw that one object. And again, if you remember the draw method from before, what we were doing is we were passing an index in, and it would dereference, if you will, each element of that array. But now we pass the object in, and we can be a little more clear about what it is we're doing. We're saying set the fill style to the object's color, set the stroke style to black, and then draw a fill rect using the object's X, the object's Y, the object's width, and the object's height. And then again, we do the stroke. And so I'm going to turn this off. Likewise with our move, when we move an object, we can set its X equal to its X plus its DX, and its Y is to its Y plus its DY. And once again, when our timer is called, we iterate across all of the objects, and we call the move function on that one object, and then we redraw everything. I've turned off the timer. We're just going to do one redraw. There we go. Now you can see all of our objects on the screen. From last time, the red square moves diagonally to the lower right, green square moves up and to the left, orange square moves from the right to the left, and the blue square is going to move as well. Let's turn on the timer. And notice how the blue square seems to be moving faster than all the other rectangles. And why is that? Again, it's an illusion. It's not really moving faster. It's just that we're changing its dx and its dy. The red square is moving with a dx and dy of 10. The green square moving with a -10. And our dx and dy for the blue square is -20. It's moving up and to the left twice as fast as the other two squares are moving. Now, that is one type of speed illusion that we have. Because it's moving faster on each move, it appears to be moving faster across the screen. Another thing we can do is change our timer. And so instead of moving every half second, we'll move every quarter second, every 250 milliseconds. We'll redraw it. You can see it moves twice as fast. So our animation speed, the ticks that we're using, everything moves on a single tick, and our ticks are now coming every quarter second. Let's move this down to 1/8 of a second, 125 milliseconds, and now it's really zooming. And if we slow this down to, say, 65 milliseconds, it'll look very smooth. This is one of the other elements of animation that if you can get your frame rate fast enough, your objects lose that jittery look. And you may have heard about this in your experience playing video games. The frame rate, if you can get it to 30 frames per second, is practically real time because the human eye can't see things much better than 30 frames a second. You may hear people talk about animations that are 60 frames a second or 120 frames per second. That means that they're computing the changes in the objects on the screen very fast. And the faster you can do that, the more realistic. Another place you'll see this is in movies. I'm going to change this back to 65. I'm going to change this down to 1. This is going to go as fast as the computer can possibly render it. In the movies, look at that. That's like happening so fast we can barely even see those rectangles moving. But in the movies, we normally see movies at a frame rate of about, I think it's 24 frames per second. Our functions are very simple. Our objects are likewise very simple. This is still not as clean as I would like because the ability to draw your object should be associated with the object itself. Wouldn't it be nice if these objects were all encapsulated into, say, a template and that we could create these objects on the fly? Our next experiment is going to be moving into the realm of object-oriented programming. And we're going to take our objects and we're going to move them into classes. And our classes then will dictate our template for each one of these objects. Welcome back. When we left our last piece of code, we had created objects, and these objects were associative arrays or dictionaries or hashes of the objects, and there were key value pairs. But there's still a niggling detail that makes this difficult to work with, and that is that the functions associated with our objects are spread all over our code. And we have things that we want to do to the canvas. We have things that we want to do to our objects. And these different pieces of code are intermingled. And so to keep our code organized And as our code gets bigger, as our program gets bigger, it's going to become more important to be organized. We want to create objects. And to do that, we're going to use classes. And a class is a template for an object. You can see that here in our old code, that we have a template for an object, right? Our rectangles have a color, they have a position of X and Y, they have a width and a height, and they also have a speed that they traverse our playfield, our canvas. But if you look down here, redraw has both elements of our canvas, our context, and also our objects. Draw, same thing. We pull the object in, and then the way that we draw the object is still intermixed with how we draw on the screen, moving something around on the screen and dealing with our timer. We've mixed all of our different objects, our canvas, our context, and our actual rectangles are intermixed, and it's hard to separate the pieces. If we want to do something more generic with this code down the road, it would be hard to tweeze out the details. What we're going to do now is we're going to move into what's called object-oriented programming. We're going to create a class or template for the playfield, which includes the canvas and the context and the timer. And then we're going to create another template or class for our box, okay? And that's going to include things like its XY location. It's going to include how to draw it on the screen and how to move it. Let's take a look at that. Here's the playfield, and playfield is a generic name for where we play our actors on the screen. And the first thing that we're going to do is we're going to draw boxes on it. We have a constructor, so when we want a new playfield, we call its constructor. We pass in a canvas ID, which is that string. If you remember from back, we do this query selector on this canvas name, and it will then go get the canvas from the document. It will then grab its context, and it creates a nice little array to store all the objects. And so this is the beginning of our playfield object. Now let's look at our box. Also has a constructor. It takes a color, an XY, a width, height, and a DX and a DY for moving it around. And then we put all of that stateful information into this box. Now, if we want to move the box, we call the move function. And notice that we're using this variable called this. When we create an instance of this box, every time we try to move the box, it knows that it uses its own version of X, Y, DX, and DY, and it dereferences them from a special variable called this. This will all make sense in a minute. Likewise, when we draw the object, we give it a context to draw onto, and then we set its fill style, its stroke style. We draw the fill rect and the stroke rect using this color, this X, this Y, this width, and this height. We really combined all of the elements of drawing a box into one piece of code, and it's very clear what our box can do. We can construct a box, and then we can move it, and we can draw it. And that's all we can do with a box. Up here, with the playfield, we can add a new object. Now notice it says object. It's not box, it's not circle, it's not square. And if we want to add it, we can add it to the list of objects that are in our playfield. If we want to do a redraw, we can clear the context, and then for each of the objects, call that object's draw method. Remember before we had an external function called draw? Now the draw method is based on whatever box we're drawing. Down here, we have a start method, which will redraw the screen and then start off our timer. And then whenever the timer is called, it will move all the objects and then redraw the screen. And move all just iterates across all the objects and call that individual objects move. If this looks weird compared to what we did before, I understand. But what we're doing now is we're creating templates for objects that we can use over and over again. Down here, this is our main code. We first create a playfield by calling new playfield, and we have to specify where that playfield is. And so when we do this, it creates a copy of this class. It fills in the blanks. We give it a canvas ID. It then creates a canvas, a context, and a list of objects for us. And then with that playfield, we now add a new box. Okay. There's our red box. and our green box, our orange box, and our blue box. And all the stateful values, the x, y, the width, height, the dx, and the dy are now added in. Each one of these objects is then added to the play field, and then I call start. Look how simple this is compared to what we had to do here. We had to, from the top down, create our objects, redraw it, create functions to redraw. We had to kick off our timer, then the timer jumps down here. And basically all of the different parts of managing both the canvas or playfield and our list of objects are spread throughout our code. But now when we use object-oriented code, we forget about what goes on inside of this box. And we can just tell it, I want this size, I want this width and this height, I want 4 of them. I'm just going to add 4 of them. And all I want to do now is to start my animation. And when it calls start, it redraws the screen, it sets the interval timer to 125, and then it calls that interval over and over again. And every time it calls move all, and then it does another redraw. Let's watch that in action. Just as before. This is a philosophical difference in how to write your code. Creating classes of objects where you have stateful information and then operations that you can perform on that object. This creates a sort of a contract with the programmer. And we can now share these objects as sort of an API or application programmer interface so that we no longer have to rewrite these capabilities. We can reuse these capabilities over and over again. And that is the promise of object-oriented programming, the ability to reuse objects without having to rewrite them every time we start a new project. Now, we still have mixed together our keyboard and our mouse and our animation capabilities, our real-time animation capabilities. And so our next experiment is going to pull this all together. We'll use our playfield classes. We're going to add our ability to select and drag objects. And then we'll also create other shapes that we can show on screen besides just rectangles. We'll move on to doing circles and ellipses. Tune in for the next series of experiments where we use object-oriented programming as well as pulling everything that we've done in the last 4 experiments together into one cohesive project. See you soon.